Track 2. All right. David Tomaschik is here to speak to you on track 2, assessing the embedded devices on your network. Thank you very much to our sponsors, the leading sponsors, HackerOne and Fitbit. It's on you, David.
Thank you. So a little bit obligatory about me. I'm a security engineer on the security assessments team at Google. Security assessments basically means I get to break things and get to break a wide variety of things. I also play a little CTF. Actually, I'm also one of the organizers of the BSidesSF, so if you haven't checked it out this weekend, you should. And I've got a bunch of certificates, but for anyone who hasn't done them, the offensive security certificates, I absolutely love those because they're not just multiple choice tests. So those are two that I actually care about putting on my resume. So insecurity of things, right? Same, it's Internet of Things, insecurity of things, about the same. Someone came up with this great idea. They're like, hey, we've got this wonderful technology called the Internet, and we have all these things that I'd love to control, and it would be so much cheaper if I could control it from the Internet. And all of this was developed at exactly the same time as we're like seeing vendors get popped left and right. We're seeing Target breaches, Home Depot, all of these things. So, of course, people are like, let's connect everything we can to the Internet. What could possibly go wrong? So why do you care about this, right? So I do a lot of black box assessment, and there's several reasons to care about it. One of them is determining whether or not a given product is a product that you want to be using in your environment. And while a black box assessment isn't going to find every vulnerability, right? Even a white box assessment might not find every one. You can usually get an idea of the security posture of the product and of the vendor that you're dealing with from a black box assessment. If it takes you 5 minutes to find the first vulnerability, you're going to have a bad time. On the other hand, some of you maybe work in red teaming or pen testing. How many people in here do red teaming or pen testing professionally? Yeah, I'm going to tell you a little bit about why you should love Internet of Things devices on the network that you're going into. There's a lot of reasons. And finally, you get this opportunity to find a bunch of low-hanging fruit. These devices are basically like pwning 90s style. So, the target audience, if you know embedded hardware and Internet of Things inside and out, I'm probably not going to be telling you a whole lot new. But if all you ever look at are software applications and you've never touched hardware, then hopefully you'll come away from this with an opportunity to break down some of the hardware that's on your network. And believe me, all of you have some of these devices on your network, even if you don't know about it, even if your security policy says you don't have any of these devices on your network. So things will look a little different from your typical assessment, right? Most of the time, if you're a pen tester or something like that, you're looking at Windows domains and Windows boxes and workstations, and you can get your foothold by client-side malware. You can get your foothold by phishing. Those are not the techniques that you're going to be using here. The techniques that you're going to be using here are extremely different from that. Almost all of these devices do not run Windows. There's an embedded version of Windows, and I've found a few devices that have like Windows XP embedded, which I don't know which is worse, Windows embedded or Windows XP, but either way, you're now full of holes. But don't worry, those only work on safety critical systems. So most of the time it's Linux on most of these devices. You'll find other operating systems. There's like FreeRTOS, which is a real-time operating system. There's ECOS. There's also VxWorks. Has anyone ever seen a VxWorks device before? Does anyone use the router provided by their ISP? 50-50 chance you have a VxWorks box sitting at home. Almost all of these devices do not use x86 CPUs. Until very recently, x86 CPUs were incredibly power hungry. Right? Atom processors have gotten a little bit better in that space, but still they're some of the more power hungry devices. So if it needs to be power limited or thermally limited or cost limited in a lot of cases, they're using a non-x86 processor. And most of the ones that I've seen have been based on ARM. MIPS is a close second cousin. I recently did an assessment of something that had an embedded PowerPC processor in it. So I got to learn pwning on PowerPC for the first time, which is kind of cool if you have the time to do it. And you usually have almost no visibility into what's going inside. You don't have a user interface like you do when you're looking at an application that runs on a desktop or a web interface. Usually the user interfaces are really, really, really weird interfaces. Like you might have a little touch screen, but more often than not, some of these devices, you have like some LEDs and buttons, and that's your user interface. So good luck figuring out what's going on under the cover from that. And finally, many of these devices are not built by companies that understand software. Like if you look at the things that are out there, a ton of these devices, and not the stuff that comes from Internet of Things startups, but like industrial control systems, they're made by industrial control systems companies. Their customers came to them and said, hey, we want a network feature. So the industrial control systems company either went online and was like, all right, we're an industrial control system company. What kind of software engineer can we hire and who wants to work here? Or alternatively, they took one of their engineers, gave them Learn C in 24 hours and said, guess what? You're the network guy now. Either way, it's not the highest quality of software that you'll find. They have typically very bad software development practices. And very often when I report issues to these companies, I go, hey, I need to reach a security engineer or security manager or something like that. And on more than one occasion, I've been routed to the guy who's responsible for physical security at their facilities. So these are not companies that are really on top of the networking game, and so I don't blame the companies entirely. So everyone should be familiar with the CIA triad of confidentiality, integrity, and availability. Right? This is how you begin your threat modeling for any assessment. And while these have many of the usual things that you'd look at any software application, they also have a variety of unusual things. You have data that you don't expect to be on there. If the device has a microphone embedded in it, you can't assume that the only audio that that device is exposed to is when someone is intentionally recording with it. You have to assume that any audio that is within range of that device could potentially be compromised by this. Likewise, some of these things have really strange constraints about their integrity. How many of you would love to know which elevators you ride in are connected to the internet? Yeah, they are. Also, industrial machinery at industrial plants. I mean, how many of you have seen reports of power grids getting hacked? Right? We're not just talking about like, integrity here doesn't just mean there's some data compromised. Integrity here means people lose power, people get injured, people could potentially lose their lives from a lot of these embedded systems. So integrity suddenly becomes a really big player. There's no going back on that. You can't restore from backup once someone has been injured. And again, availability is a big thing of that, right? Like, what if you found a bug that was just a denial of service in an elevator controller? It's still pretty traumatizing to lock someone in an elevator until the elevator repairman gets there. So I want to go through this and talk about the techniques that I've used to assess things using a case study. This is a voice over IP phone. It should be pretty reachable. Most of you probably have one of these, maybe not this particular brand, but have probably seen some of these in your environment. And it's still a network-connected embedded device. So how do we find out something about this, right? If you're doing an assessment, the first step is always to do some recon. And it turns out that anything that has a wireless chip inside of it that's sold for commercial sale in the United States has to be approved by the FCC. And part of that approval process is to stick a sticker on the bottom that has the FCC ID on it, which you can see on this sticker in the bottom right corner. And then you can go look up things about it, like what bands it uses and other useful information. There's a wonderful website, fccid.io. It's not the official FCC website. The official FCC website is pretty bad. This site makes it much more usable. There's other ways that you can find out what's going on. Read the user manual. I know we all hate reading manuals, but it turns out you find surprising things when you read the user manual. I made the mistake of not doing this in an assessment once, and we were looking at it for a while. And then I get to the page where it says, if you've lost your password, you can use this username and password to reset the passwords on the device. Hard-coded creds in the user manual. Way to go. Also, grab the firmware from the website. If they provide firmware and you can download it, you can grab it from the website and you can do all kinds of things with the firmware right there. You have the files that are on there. So many of you probably are familiar with encrypted firmware and the possibility that you could do that and encrypt firmware before it's downloaded to make it harder to reverse engineer. Anyone care to take a guess how many times I've found encrypted firmware for a device? Yeah, everyone who said 0, that's correct. Nobody encrypts their firmware. So this is from the FCC database. This is a picture of that same phone from the inside. You can't see it very well on the slides here, but you can actually blow this up and find out exactly what CPU it uses inside. It's an ARM CPU. And you can find a bunch of other potentially useful things off of it. You can find the model of flash that it uses, the model of RAM that it uses. You know how much RAM and flash it has. What's interesting about knowing how much RAM and flash a particular device has is you can narrow down the operating systems that you might be looking at. If it has like 2 megabytes of RAM, it's not even running Linux. It's maybe running VxWorks or FreeRTOS or something like that. So from the firmware, there's a wonderful tool out there called binwalk, and what that does is it goes through a binary blob and extracts other known file types from within that binary blob, and it gets you all of these files out of it, and you can use it, and it'll even find compressed files that are inside that. So like the firmware might be a GZ with it with some special header on it, and it will find this, extract the gzip, and give you the raw file. And then I love to just run strings on it, right? I mean, strings is a wonderful tool for getting your feet wet and getting your orientation to it. And so I'm doing this, and I've probably been looking at this device at this point for a total of 2 hours. And I run strings on the firmware, and I find these strings here. And I don't know about anyone else, but if you've ever seen command injection, this is what command injection looks like. They're like, oh, I don't want to actually make my program talk directly to the Wi-Fi interface. That's kind of hard. I'm just going to use the command line tools to do it, and we're just going to pass parameters on the command line via like sprintf style strings. So yeah, that's a good place to start looking. So then I like to go live, right? And so this is that target board. I've taken the back off of it because reasons that we'll get to in a moment. And I plug it into my laptop, and I actually use 2 USB network interfaces and put a VM on my laptop to man in the middle all of the traffic coming off of a device. Because then you can see everything that's going through it. Even if you don't actively man in the middle SSL, you then know what hosts it's connecting to. You know whether it's reaching out and downloading firmware on first boot. You know whether it's reaching out and grabbing config on first boot. It's really useful to do this like from straight out of the box, do it on first boot, because you can see a number of steps that it may never repeat. The reason I have the second network interface, and I'm not just depending on it, by the way, I didn't want to put the other end of this connection onto our corp network, so the other one goes into a lab network instead of going out to our corp network. So if you have a suspicious device, you may want to consider doing something like that if you have a similar setup. And so it isolates traffic from your testing host when you're in your VM, right? So the boot up, like I said, is very interesting. Maybe you want to man in the middle HTTP or HTTPS. Burp Suite, anyone? It's wonderful for that. It's also interesting when you start seeing all the HTTPS traffic flowing and you realize you didn't install a certificate on the device. They're not verifying certificates. Then I like to use Nmap, right? Nmap is one of my favorite tools in my toolbox anytime. And I scan all the ports. This is sitting one network cable away from my device. I'm not worried about traffic. I'm not worried much about dropped packets. That's why it's T4 and not T5. And turn everything on. And maybe you want to turn on Nmap scripts. I actually had an interesting experience with this particular device thanks to Nmap scripts. The first time I ran Nmap on it, sitting there watching it, waiting for the results to come back. It takes a minute or two. And about halfway through the scan, the device reboots. It's like, well, that seems interesting. Let me see if I can reproduce that. Run Nmap again. The device reboots again. Run Nmap again. No, this isn't a fluke. The device is going to reboot every time I run Nmap. So it turns out that I found a crash just by running the Nmap scripts that triggered the device to reboot. The hardest part of all of it was narrowing down which Nmap script was running at the time the device crashed. By the way, Wireshark helps with that. You watch in Wireshark and see what packets are just sent when the device crashed. So let's talk a little bit about like the most basic hardware tricks, right? So this particular one was actually super straightforward because on the board there are these 4 pins sticking out of there. So how many of you have actually used a serial port in your life? Oh wow, that's actually more than I expected. There's a lot of people, even in this industry, that I say serial port and they go, what? So a serial port normally has like 9 pins on it, but it turns out you really only actually need 3 pins to communicate. All you need is ground, TX, and RX. And there's this wonderful adapter you can buy. want to connect directly to a hardware serial port, by the way. Hardware serial port is 12 volts. This board runs at 3.3 volts. You put 12 volts into a 3.3 volt board, you will let out the magic smoke. Your assessment will be over until you buy another device. But this little cheap USB to UART adapter, I think this one's from Adafruit, maybe from SparkFun, something like that. They're like $6, $7. People use them to program Arduinos. So it's a totally useful tool, and you can connect it right up to that. And you don't ever want to connect the voltage output line. You don't want to drive the board from two different voltage sources. So you plug the board into its own power supply, and then you just don't connect the usually red wire, as you see in this case. You also, if anyone's ever used a bus pirate, you can also use a bus pirate to achieve this, but you have to go through like 8 levels of menu in the bus pirate to get to this. So even though I have a bus pirate, I much prefer using this for UARTs. So knowing the pinout, though, is important to being able to connect it. There's a bunch of different ways you can do that. So the first pin you want to identify, partly because it's easiest and partly because it's the most important, is the ground pin. And it's actually really easy. You get a multimeter, you set it to resistance mode, and you touch one of the probes to anywhere that you know to be ground, which is, for example, this particular device had some USB ports on it. The outside of a USB port, the metal chassis, is always grounded. So touch the multimeter probe to that end, and touch the other multimeter probe to each of the pins that you're investigating. And when you find 0 as the reading, 0 resistance, you know that you have found a pin that's connected directly to ground. So identifying the ground pin is usually straightforward. Identifying the rest of the pins can be a little tricky. So on most devices, I've never had one have a problem with this. Most of the time, I'm lazy. I try the RX and TX one way. If it doesn't work, I swap the RX and TX, and then it usually works. That's the lazy way to find it. There's usually not a problem with that. They're not sending enough current to cause damage if you have them backwards. But if you want to be proper about it, if you want to do it the right way, you hook up an oscilloscope or a logic analyzer or something like that, and you can actually see the traffic coming across here. So at the bottom here, I have an open source tool called PulseView using about $20 from China cheap logic analyzer that's just an FPGA basically. And I'm actually extracting the data from the UART. And there's 2 channels there. One of them's completely flat, and one of them has rise and fall of signals. And that rise and fall of signals tells you that's the one that's transmitting from the board that is your target, essentially. And also the logic analyzer is great because it'll help you figure out the baud rate, right? Serial ports can be configured at a number of different baud rates. And I've seen on embedded devices, I've seen 9600, I've seen 19200, I've seen all the way up to 115,200 or whatever it is in terms of baud rates. I've never seen faster than that, but manufacturers typically just pick. And so again, this is something you can do by trial and error. Or if you use the logic analyzer or oscilloscope, you can actually just see when the rise and fall are occurring and figure out the baud rate. PulseView is nice. There's a script that will actually take the data from PulseView, calculate the widths of the bits that are going across the network, and tell you what the baud rate is. So you don't even have to do any math or anything like that yourself. So this is a particularly useful UART. I hooked up to it and let the device boot. And I get all kinds of boot messages. You can find out a ton about the hardware. And I got to a login prompt at the end. And I was like, well, it doesn't hurt to try. I'll guess a few obvious passwords. And so I typed root in, and it didn't ask me for a password. Obvious password is no password. Which really isn't the worst thing ever because they don't run an SSH server or anything like that. I mean, this is entertaining. But in and of itself, it's not really a vulnerability because if someone has hooked up a UART to the device at in your facility, you've lost at that point anyway. But it's just really amusing. Sometimes it's super easy like this because then at this point you're like, oh, I have a root shell. I can do whatever I want to investigate this device. If you get this on a device and you don't have a firmware download or something like that, you can use DD and read from the raw flash device, and you can create your own firmware image from the device. Which is super useful if you're not able to find a download firmware or something like that. The other benefit of having a shell while you're on it is you can find out what happens when you are interacting with the device. So at that point, I wanted to do some sort of fuzzing or something like that, right? Like a lot of bugs these days are found by fuzzing. I'm lazy. Letting a tool find my bugs for me is, in fact, the way I like to do it in a black box assessment. And one of the other nice things is fuzzers just sit there and run. You can start a fuzzer, and then I can go back to IDA and do my manual assessment in parallel with the fuzzer and be finding bugs at the same time. But it turns out, like, normally I spin up a fuzzer on my workstation or spin it up on a server or something like that. Pretty straightforward, but in this case, you can't do that. First off, it's an ARM, so I can't run the binary natively on my workstation. Secondly, even if I try to run it with QEMU or something like that, it fails at a bunch of different points where it's trying to open device drivers for the devices that are built into it. And I was like, well, at this point I have two options. I can either figure out how to patch around all the device drivers and then figure out which of the bugs that I find are caused because I just made device drivers return null, or I can try to fuzz it on the device. And this is the first time I ever tried to fuzz something live on an embedded device. And I was like, this can't be too hard, right? So it turns out, actually, the reason it rebooted every time I scanned it with Nmap is they installed a SIG-SegV handler. And the segfault handler rebooted the device every time it segfaulted. And I was like, well, that sucks. Every time I cause it to crash, the whole device is going to reboot. How am I going to get any state off of that? How do I capture the state of the crash so I can figure out like what the source of the crash is? So the first approach that I took, I cross-compiled GDB server for ARM, stuck the GDB server on there, and started and attached it to the process. And so instead of getting to the segfault handler, GDB would pop up on my workstation, be like, oh, you have a prompt, segfault was captured, you can get a backtrace, you can inspect the stack, all those nice things. But that meant I had to do it in real time. I had to sit there with GDB open and like actually do something every single time it crashed, and then the device would still reboot as soon as I continued in GDB. So I had to wait for the device to boot again. And so I was having this manual process, and that's not automation. Like, fuzzing is supposed to help you, not make your life harder. At this point, I had made my life harder. So we tried a second approach. We decided to modify the binary, get rid of that segmentation fault handler, and use the core pattern support in the Linux kernel. Anyone familiar with this? So the Linux kernel writes files called core files whenever a program crashes. And by default, it just names these core and stores them locally. This particular device, I think, actually redirected them to dev null because you don't really want to store core files on a small embedded flash drive. But it turns out there's a cool feature where you can start this file name with a pipe character, and you can pipe it to an arbitrary program. And so what we did is we piped it to netcat to send the core file, off to my workstation. So I just started collecting core files from this when I was going through it. And so in this case, it was just netcat to the workstation on like port 9999, and then on the other end, I had a little bash script that really did like netcat-l out to a file and then put that in a tight loop. So I was doing this, and then I got a bunch of core files, and it turned out that if you start fuzzing an embedded device, you get a lot of core files. I let it run over a weekend and came back to find that the disk on my workstation was full. Now, it turns out that doesn't mean that I found like 10,000 bugs, right? That would be really awesome if you found like 10,000 separate unique bugs, but I'd probably still be trying to categorize and report 10,000 bugs from this assessment. So it turns out that basically it was just small variants on the same crash repeatedly and repeatedly, or same, I should say, about 6 crashes repeatedly. So I ended up having to write a script. There's a bunch of them out there that already let you sort through core files and sort them based on where it crashed and things like that, except I discovered a bunch of these are hard-coded to look at EIP or RIP, which are the instruction pointer names for x86 and x86-64. And ARM does not call its program counter EIP or RIP. So some of these scripts categorized all of them as the same because every time they tried to get the value of EIP or RIP, they got nothing. So it turned out that I ended up writing my own script. I could have fixed the other ones that were out there, but at the point I was trying to categorize them. And so I was grouping them by where the program counter was and what the stack registers were at that point, the stack pointer and base pointer were. And so I started grouping them and then doing script analysis of these core files. And it ended up being, actually, this fuzzing process was so relatively fast that I was still the slow part of the fuzzing process, even though I was doing this on bare metal on a CPU that runs at something like 48 megahertz and piping the core files over the network. And all of that, I was still finding enough results that I was the slow part when I was analyzing the core files. So there are some more advanced techniques that you can use. JTAG is this really cool thing built into most embedded processors. It stands for Joint Test Action Group. So a bunch of processors in the early days had like various debugging mechanisms that were inserted into them so that you could do live debugging on the chip. But it turns out that these live debugging mechanisms were all different from every processor to processor, sometimes even within the same manufacturer. And so they came up with a standard way of doing this, and it takes something like 5 or 6 pins to do it, but you can actually inspect the live state of the processor, which means you can even investigate like kernel crashes using this technique. The downside is finding JTAG pinouts is really hard, because even though they standardized the electrical aspects of JTAG, they didn't standardize the pinout, and so the connector can be 6 pins, it can be 20 pins, sometimes it's little test points on the board. You have to be really kind of dedicated or insane to go after JTAG on something, unless you really are a hardware guy. But another thing that's actually not too hard is to dump the flash. There's little clips you can get that clip directly to the flash chip, and then you can use a tool like the Bus Pirate to actually dump the contents of the flash memory of the device, and so that's another technique you can use to get the firmware off of the device. So if you can't find a firmware image, and maybe you either can't get a shell via the UART, or maybe they've actually set a real password, this is another possibility for getting access to the flash memory. And then if you really want to be clever about the things you're doing, you can modify the firmware extensively and replace files in the firmware and rewrite the firmware and do things like that that give you more insight into what's going on in the device. But we had a little bit of a problem when we tried that. So I mentioned modifying the binary. It turns out that this particular device uses a file system that compresses all of the files, which that sounds great. You want to use as little flash as possible, sounds great. I modified the binary. I put some NOPs in place of actual instructions. The binary was exactly the same size, byte for byte, and then I tried to write it to the file system, and it says no space left on device. So it turns out that the compression mechanism that they use is different when you build the file system as an image initially versus when you're replacing a file in place. Because when they build the image initially, they have a compression algorithm that goes across the blocks of the entire file system, and it can compress more efficiently than when you're using a file system and you're just writing to it at the end, because then it's only compressing across that one file. And so it turned out that you cannot replace a file with a file of exactly the same size on this file system. And it also turns out that this device completely refuses to boot if you try to reboot it without that program in the file system. Like, it doesn't even get to the UART. So this brings you to a lesson. If you're going to do this and start replacing files in your flash or otherwise modifying the device you're using, you might want to have more than one of the devices. Because there's a non-zero chance you're going to brick the device. And depending on how long you've been doing this for, the chances of that, at the beginning they're pretty high, then you start doing this for a while, they go down. And then you go, you know what, I'm good at this. I can start soldering directly to like test points on the motherboard and all kinds of other crazy things. And it turns out your failure rate starts to go back up. So there's a bunch of different advanced techniques you can take to this, like you can go really crazy. But if you're not a hardware engineer and you've never done like any sort of hardware things, if like the idea of using a multimeter at the beginning of the talk was a little scary to you, maybe you don't want to be trying to like desolder chips to read them. But like the rest of the techniques should be applicable, and like I found several bugs in this particular phone using this. Multiple memory corruptions, which are always cool to find. Command injection, I probably could have found the command injection during just black box testing of the application. I would have eventually found it, but running strings on the binary said, oh, there's Wi-Fi things. Let me try putting commands in the SSID. Oh look, backticks in the SSID work, done. This particular one, this one would have been easy to find without any special techniques. They had no cross-site request forgery protection at all. No effort towards cross-site request forgery. And they also implemented HTTP digest authentication, except it's kind of like they did it by looking at what the absolute minimum is to get a browser to interact with the device, and not looking at the spec or anything like that. So the spec says you're supposed to do a bunch of different things for digest authentication. You're supposed to generate a nonce that's, like all nonces, used only once. Then you're supposed to verify that the response that comes back has the same nonce as the one that you sent. You're supposed to verify that the URI in the signature matches the URI that's actually being requested of the website, and all these other things. Now, this basically broke down to about like HTTP plain authentication, because none of that was checked, none of the extra features. It was basically take the MD5 sum of the username and password and send it back, and it was approximately that. So you can find a bunch of different bugs this way. It's just a one device. So at this point, I think I've got like about a little less than 5 minutes left. I can take a few questions. And I'm on Twitter, and I have a blog that I occasionally post security relevant things to. Yes?
What is the most bizarre hardware device you've ever had to work on?
The question was, what is the most bizarre hardware device I've ever had to work on? And the single most bizarre one is one I can't talk about. There's several projects I've worked on that I either can't talk about right now or can't talk about for a period of 90 days per disclosure policy. But most bizarre devices I've worked on I will say they were industrial control systems of some sort. It turns out industrial control systems, guys, they really are just like, oh, just build a separate network that's air-gapped. Which, okay, it's not the worst thing you can say, but Stuxnet kind of proved that even in a highly secure environment with an air-gapped network, you're still going to get malware. And secondly, like, we generally, like, no one actually wants to air-gap their network because that takes away 95% of the convenience of networking in the first place. Any other questions? Oh, sorry. Don't know. The question was if there's any off-the-shelf software that you can use on like your home network to see for known vulnerabilities. I don't know of anything specifically that's related to like IoT devices. You can get like the free version of Nessus, like OpenVAS, which will let you can scan your network, and it has signatures for a bunch of known vulnerabilities that would cover IoT devices. It's also quite enlightening to just run an Nmap scan of your entire home network if you have a bunch of devices like this, and see how many ports are open, because it's really bizarre. You have I've found some devices before that had like upwards of 100 listening ports on a single-purpose device. I couldn't figure out what they're doing unless they're just like looping over all the ports to then try a UPnP forward or something like that. I don't know, but it's really bizarre. All right, well, thank you very much. If anyone has any questions, come find me. I'll be in the CTF room most of the rest of the con, so if you want to talk about Internet of Things, I can do that practically the entire con. So thank you very much.
Thanks very much, David. Fitbit would like to thank you as well with this speaker gift. So thanks very much.
Thank you.
All right, everybody. Don't forget the party tonight at 8 o'clock. There's also a resume right